Okay, the last presentation in this morning's session on Edge AI is from Innatera, another new company that is speaking for the first time in detail about their architecture here at our conference. Our presenter will be Sumeet Kumar. Sumeet, you can go ahead and turn on your microphone. Sumeet was previously with Intel. He worked on imaging and camera technologies, developing complex media processor architectures. And he also has done work at Delft University in the Netherlands on various European R&D programs for energy efficient compute hardware and for autonomous vehicles. So looking forward to your presentation and your disclosure of your architecture for the first time. So Sumeet, you can go ahead and turn on your screen sharing and we'll talk again in the Q&A.
Thanks for the introduction, Mike. I hope you can hear me and see the screen clearly.
Sounds good.
All right. So good morning, everyone. Today I'm going to be talking to you about ultra-low power pattern recognition with spiking neural networks. This is a brief outline of the talk for today. So I'll first start off by introducing you to some of the challenges of processing sensor data at the edge. And I'll walk you through how the brain addresses some of these limitations in the form of its own spiking neural network and how it implements pattern recognition so efficiently. I'll then take you through Innatera's architecture for accelerating spiking neural networks at the sensor edge. Our architecture is called the spiking neural processor, and I'll take you through some of the key design objectives that we had in mind and the actual architecture itself. I'll finally take you through a few applications that we mapped onto the spiking neural processor, and I'll give you early numbers on energy and the kind of performance that we achieved. Finally, I'll leave you with a preview of our software development environment, and thereafter we go into the questions. So first things first, picking up from the first presentation, the keynote presentation of today, we looked at this entire inference value chain of sensor to the data center. And when we actually look at how machine learning and AI are applied across this value chain, this is roughly the chain that we see. On the extreme left, you have the sensor, which produces data. And on the extreme right, you have the data center, where many of the really heavy machine learning algorithms are really run. What we also see is that as you move away from the data center and go closer to the sensor, the kind of applications that are typically run on these machine learning and AI processors becomes more specific. And as you get very close to the sensor, you start to see very specific applications once again. And here we're mainly looking to condition sensor data, understand its relevance, identify patterns inside of it, and carry out very specific classifications which would reduce the amount of data that we're streaming to the data center. Now, as sensors become more pervasive and they go into more edge use cases, typically what we see is that power tends to be heavily constrained, either due to limited battery sizes or the small size of the device into which the sensors are integrated. But beyond this, because many sensing use cases involve human-machine interfaces, we also see that latency is extremely critical. So very close to the sensor and inside of the sensor, we're commonly looking at sub-milliwatt power budgets for inference, or in more complex sensors, sub 10 milliwatts. And to do very heavy processing inside of this is extremely challenging. Now, when we try to take inspiration from the brain, we actually see that it's very efficient at doing multi-sensor data processing, low latency pattern recognition, and it's generally very energy efficient as well. This is a video of the neural responses from a zebrafish larva. And what you'll notice here is that time plays a very central role in how the brain processes sensory data. So what you notice is this particular larva is being stimulated by light from different angles, and you find different groups of neurons responding to the different stimuli, and they respond in a very deterministic manner. And apart from the spatial response, what we also very clearly note is that there is a distinct temporal pattern in how these neurons fire. And this temporal pattern seems to be very key in how the brain efficiently processes information. And in order to mimic that, we have what is called the spiking neural network. This is effectively an artificial neural network within which information is encoded in the form of precise spikes. Now, information essentially exists in the form of digital pulses, 0 or 1, and the key is that the information is encoded in when these spikes occur. Now, to visualize this, you can think of these spiking neurons as being integrators. They essentially, when stimulated by an input, they get charged up. And if you stimulate these neurons enough, they reach a certain threshold at which they fire a spike. Now, it's the sequence of these input stimuli and their strength that effectively determine when these neurons fire. And that is the fundamental principle behind spiking neural networks. Manipulate and somehow change the timing of spikes and leverage the correlations between different spikes inside of the network in order to condition data, in order to recognize patterns and basically classify it. This is essentially what we also do with spiking neural networks for pattern recognition. On the left side, we provide input data, which is then encoded into a spike-based representation that is processed by our spiking neural network that creates a certain signature. That signature is then characterized at the output, and based on that, we know what kind of patterns were in the input data. This is fundamentally the same principle that we leverage inside Innatera's spiking neural processor. This is effectively a brain-inspired processor that enables turnkey pattern recognition in applications where power is limited. It effectively allows you to analyze sensor data in real time to detect and identify patterns of interest. These patterns can be spoken words inside audio data from a microphone, it can be objects inside radar data, or it can be faces inside image data from a camera. The spiking neural processor is essentially an accelerator for spiking neural networks. It implements spiking neural networks in a massively parallel real-time fashion using an analog mixed signal array of neurosynaptic components. This array effectively contains small circuits, the neurons and the synapses, that effectively mimic the operation of biological neurons and synapses. And because these circuits are implemented in the analog domain, this is essentially what allows us to deliver energy efficiency and latency when actually, low latency, when actually implementing spiking neural networks in silicon. The architecture looks a lot like the pipeline that I showed you a few slides ago. On the left side, you have the standard interfaces that connect to sensors through which data is streamed into the architecture. This data is converted into the spike form using a bank of data to spike encoders, and the spike-based representation is then streamed into the analog mixed signal neurosynaptic array, where the spiking neural network inference actually happens in real time. The results of that inference are passed to spike decoders, which then tries to figure out what exactly happened in the network. And based on that, we figure out what patterns were in the input. And this is sent out either to an applications processor or to a controller that's waiting for these results. Now, if we focus on the central part, that is the neurosynaptic array itself, the key design objectives that we kept in mind were that we were looking to build a native accelerator that could reproduce the continuous time dynamics of spiking neural networks. This temporal capability of these networks to process data is by far the most powerful paradigm that we wanted to leverage, and this is the #1 thing that we kept in our list. Now, moving up, we wanted to target the sensor edge space, and this required an energy efficient fabric, and we chose to go the analog route. And when you go down the analog route, it's important to dimension your system for predictability and controllability. So this was, again, at the top of our list. And finally, we wanted an architecture that was flexible and configurable enough that algorithm developers could map a diverse range of complex neuromorphic neural networks onto the architecture without any loss of capabilities. So we'll first start with how we architected the array itself. The elephant in the room, of course, is that we are an analog fabric, and anytime you have analog components, you normally have the challenges of mismatch and variability. And in order to address this, we broke down our array into small manageable pieces, which we call segments. Each segment packs in a group of neurons and synapses, and these segments themselves are dimensioned in such a way that we have close control over how the individual devices are sized and how the different interconnects are actually dimensioned, such that we get regions of very uniform device behavior on chip. Every segment can effectively implement its own spiking neural network, or it can execute a part of a larger model which is mapped onto it by our SDK. If we zoom into each one of these segments, what you notice is that it has an analog mixed signal array of synapses and neurons, and these are organized over a multi-level crossbar structure. We chose this structure again to offer a great degree of flexibility and connectivity options to algorithm developers to connect different neurons with one another. These switch matrices that you see at either end of the crossbar array effectively allow us to offer very high fan-in, fan-out, especially when you have these fully connected layers, even inside the spiking neural networks. These matrices allow us to really spread these connections out. Right at the bottom, you notice you have the spiking neurons, and every column of synapses drives this bank of spiking neurons. Most notably, you will see that the inputs and the outputs of every segment are essentially these binary spikes. One of the disadvantages of conventional artificial neural network accelerators, especially the analog ones, is that you often require a whole bank of DACs at the input and ADCs at the output, and with every compute step, you're constantly doing multi-bit conversions. Because we're using these single-bit spikes, we don't have those kind of difficulties. But to go one level deeper than that, the synapses themselves are analog compute elements. So every synapse is effectively an event-driven component which contains two parts. One is a weight storage element, and the second is effectively an analog multiplier. And its key function is to multiply the incoming discrete spike events with a certain reference voltage, which is essentially controlled by the amount of weight that is stored in the weight storage element. The purpose of the synapse is to implement an efficacy or an efficiency of a connection between two neurons. And each of these synapses, once multiplied by this reference voltage, then results in a current which then goes and charges each one of these spiking neurons. Now, it's very important to note that the actual DAC and the weight storage element only consume power when they're initialized. Thereafter, they don't switch at all. And for the entire duration of inference on chip, they're only consuming static power. It's because of this that we actually have a very small energy per synaptic operation characterized in 28 nanometer silicon. This is about 200 femtojoules, and that's about 63 times lower than a competing digital implementation. These same benefits also extend into our neurons. We use conductance-based neurons, which offer us very rich temporal dynamics and neuronal behaviors. They allow us to implement a great degree of signal processing functions due to the fact that they have such rich expressions of neuronal behaviors. Now, the reason why we chose an analog implementation here is that the continuous time response is best captured by an analog circuit. And in the discrete world, you tend to lose a lot of this resolution, and effectively where you pay for it is in the amount of information that is encoded into every single spike. So in the analog world, we're able to pack in a lot more into every single spike as compared to the digital world. Our neurons themselves are conductance-based, which means the parameters are exposed to algorithm developers directly in software, and the developers can then tune these dynamics and these neuronal behaviors from their algorithm. And these are actuated on chip with biasing and control circuitry, which are integrated alongside these neurons and synapses. This gives us a great degree of fidelity in the kind of responses that we can actually see in our spiking neurons. Here as well, because of the analog implementation, again for 28 nanometer silicon characterized, every spike consumes less than 860 femtojoules, which is once again above 60x better than a digital implementation. Now, in constructing the overall array and stitching together these different segments, we used a hierarchical approach, and we followed the interconnect paradigm that the brain does. You have regions where connectivity is dense, and then you have less dense global connectivity. And the rationale here is that neurons which are close together often talk very much to each other and are densely connected to each other. Those far apart communicate less often and have less or have more sparse connectivity. The same paradigm reflects in our interconnect structure, where we have two distinct interconnects. We have a short-range interconnect, which is dimensioned for highly dense connections and low latency communications between segments. And we have the long-range interconnect, which is dimensioned for more sparse connections, but those requiring higher throughput between distant segments. For the short-range interconnect especially, we use the address event representation. So this is effectively a representation wherein the spikes are converted into a neuronal address, and it's this address that is then routed as a packet. And this allows us a great degree of flexibility in routing that spike even to more distant segments. For close-range communication, we use a single-channel parallel AER link, and this is really dimensioned for broadcasts between segments. So if you need to do a high fan-in, high fan-out connection that spreads across different segments, you would do it with a broadcast. And because this is really baked into the architecture, you don't require multiple transmissions from the source. In addition, this channel is also dimensioned for balanced transfer latencies between the different segments. On the other hand, the long-range connections are implemented over a bundle of bit serial AER channels, and the size of this bundle is optimized to ensure high throughput and very predictable latencies regardless of the distance that you're actually traversing on the chip. Very important to mention here is that the actual connectivity and the implementation of those configurations themselves is flexible and can be done at runtime. So the synapse to interconnect bindings are completely configurable. They are not hard-coded into the system, and you can link any neuron and any synapse to the different interconnects dynamically, depending on the network that you have. One of the first applications that we mapped onto this architecture was a traditional audio processing application. So this was a spoken word classification exercise where we were essentially looking for 11 different words in a combination of clean and noisy input data. And we did this with a two-layer, fully connected feed-forward network, which was completely spike-based. We had two different forms of this network. The small one used about 160 neurons in total, and the large one used about 610 spiking neurons in total. And these networks were effectively operating on 8 kilohertz, 12-bit sampled audio inputs. And regardless of the amount of noise that we had inside of these inputs, effectively what we saw was in each case, we had roughly 500 spike events until the point that we could actually classify the data. So effectively, we were doing sub-millisecond latency classification, and in total, we consumed only about 500 spikes. Now remember, each spike only consumes a few hundred femtojoules. So in total, effectively, what you're looking at is a dynamic inference power, which would be measured in the low hundreds of microwatts. A more recent example as well is something which we are currently working on together with an early customer. And this is a complex sensor within which you actually have a data stream in real time containing spatio-temporal patterns embedded inside of it. And on the left side of your screen, what you see is a video which shows the real-time response of spiking neurons, which have been organized into a liquid state machine topology. And what these neurons are doing is they're responding in a temporally locked fashion to the patterns that they're seeing at the input. On the right side, you have a spike raster that really shows this response over time. And you can clearly see the 6 different patterns present themselves in the 6 different spiking responses of the network. We compared this with a conventional implementation that ran on a DSP, and also on a competing implementation where we were looking at an emerging AI accelerator. And compared to both, we had a 40x lower inference latency and up to 49x lower inference energy compared to these alternatives. These are demos that we'll be doing later on in the year, so I hope to be able to share more with you as we go forward. Both of these applications were realized using our spiking neural processor SDK, and the objective of this SDK effectively is to simplify the development of spiking neural networks and make it much easier to deploy them into applications at the sensor edge. Within this, you would describe your model essentially at a high level using standard Python. You'd be able to compile that and effectively map the resulting binary onto our chip. And on the other side, you would also be able to explore different algorithmic approaches, different training methodologies, and in general, from the advancing state of the art in spiking neural networks in order to validate performance of your solution and arrive at a trained network, which you can then map and deploy in large volumes. This is the SDK we'll be releasing, we'll be talking more about and releasing in the second half of this year. We are currently working together with select customers on a number of very exciting use cases. And as we go forward in the course of this year, we'll also be doing more application demonstrations. We'll be sampling the first pre-product prototypes to early customers and research partners in the second half of this year. This includes both the silicon as well as our SDK. And around the same time, we'll also be announcing the specs of our first product, which will release in 2022. We have a number of new application use cases which are currently in the pipeline, but we're always scoping out for more. So I leave you with this question: what new applications and use cases will our spiking neural processor unlock for you? This is a question that you can answer, and we'd be very glad to hear from you. We have a breakout session immediately after this, and we'd be very happy to see you there. Thank you.
Okay, thank you, Sumeet. You could go ahead and turn off your screen sharing, and we'll go to the Q&A. It's a very interesting talk. As a former analog IC designer myself, I find it to be particularly interesting. And it does seem like you truly do deserve to use a neuromorphic description, because you are modeling some of the biological characteristics of neurons. Mm-hmm. Wondering, you said that you're addressing some of the mismatch issues by locality, but you can still have noise and other issues across the array. Do you have to do any self-calibrating, other kinds of things to compensate for that?
Well, we deal with these non-idealities in multiple different ways. So the first way we did this is really by carefully dimensioning the devices themselves. And when I say that we dimensioned every single segment, what I mean here is that we dimensioned the devices for the signal-to-noise ratio. Mm-hmm. But coming one step above that, you notice that the overall array is a hierarchical array. We have a large number of segments, and we can actually make use of multiple segments when we're mapping large networks on top of these to kind of average out these effects. But at the end of the day, all of this is a trade-off between power, between accuracy, and between the kind of signal-to-noise ratio you can actually tolerate for your application. And within all of this comes the story of calibration. And because this is essentially a configurable device, you can actually take the design point into different spaces depending on the kind of application that you're targeting.
Mm-hmm. Mm-hmm. You use 28 nanometers as an example. Is that the target process that you're looking at for your chip?
Yes, this is the process technology that we're going forward with for the product.
Okay. Could you say how many neurons you're looking at having on chip?
These details we'll go into in a little more detail in the next 2 quarters. But in general, because these are spiking neural networks, we don't expect to be packing in millions of neurons or even hundreds of thousands of neurons. We'd be looking to put in a more reasonable quantity. And from our experience with what we've seen with true neuromorphic solutions built with spiking neural networks, you don't actually require all that many neurons.
Okay. We have a few questions coming in from the audience. Please go ahead and submit them. We have time left in the Q&A session. First question is, I'm not sure if this is a question or an opinion, but it says, analogous to PCs and CPUs, we think that going forward, there'll be a consolidation of AI architectures. Do you think that spiking neural networks will be one of the prevailing architectures? I think there's been a lot of research here, a lot of people claiming neuromorphic architectures. We haven't seen too many in production yet. I think we're just seeing the first now with BrainChip, for example. R&D from Intel. So what's your opinion on that? Obviously, you're banking the company on this architecture.
Well, spiking neural networks are not new at all. And what we've seen is an increasing acknowledgement of their actual place in the overall AI value chain. And what we're also figuring out is that they actually would do very, very well at the sensor edge. It's important to recognize that you should not necessarily be using spiking neural networks in all of the same applications that you would throw a CNN or convolutional neural network or every other artificial neural network at. These networks are good for very specific tasks. They're very good at processing raw sensor data. They're very good at doing pattern recognition. But they should be viewed very differently as compared to conventional ANNs. So I do expect that as the edge infrastructure or the ecosystem for edge processing grows, and as sensors become a little more pervasive in these edge use cases, we'll also have an evolution of the kind of SoCs that we see at the edge, going beyond traditional microcontrollers. And I definitely think that spiking neural networks and spiking AI in general will form an intricate part of the sensor, as well as the processors that sit right next to them at the edge.
So yeah, smart sensors sounds like a great application. And you showed an audio example. That's low data rate. Is that what you're going for here? Low data rate sensors?
That's one of the examples. So audio is a really hot area. This is an existing market which has very critical problems that exist even today. And there's a very strong reason to put spiking neural networks in there, because they can do a lot more than classification alone. There's a whole bunch that we can do with signal processing and signal conditioning. And these are avenues that we're exploring together with these spiking neural networks. But we're also applying them to more complex sensors. And this was an example that I showed, the second use case that I showed you. This is by no means a low data rate sensor. This is quite an advanced sensor, which is going into increasingly low power use cases. And we are targeting processing of this sensor data together with the SNN as well. So you can do a lot more than low data rate processing. And we will be showing how power efficient that is in the later part of this year.
Great, yeah. Some more questions from the audience. Can you elaborate about the short versus the long range connections? When would you use either of those?
Definitely. What we often see is that once spiking neural networks are trained, you have regions or you have neurons which are very densely connected with one another. You have populations of neurons that talk intensively with one another. And then you have other populations which are more sparsely connected. It's these dense connections that we would map onto the short range interconnect, especially connections that are latency sensitive and have very low delays, and where you require extremely predictable low latency communications. That's what goes on to the neighboring segments. And those where we don't really care too much about latency, those where communication can be sparse, where we can afford to have a higher delay, these we place into more distant segments.
Okay, next question I was going to ask also about the training. How do you do that?
There are a range of different options. And at the outset with spiking neural networks, one of the advantages is that you can use unsupervised learning techniques as well as semi-supervised learning techniques that really depend on the exact timing of these spikes. And that's a very powerful way of training these neural networks. Now, all of that power that it offers also comes at the cost of complexity. And in the short term, we see a lot of algorithm developers choosing to do a more supervised approach. Now, you're correct that backprop cannot be used in its direct form. You don't differentiate the spikes, but you can use variants of backpropagation that don't use the spikes themselves, but for instance, use the membrane voltage of the neurons. That definitely is differentiable. And there are a number of emerging backprop-based techniques which go down that same path. And that provides a very promising way forward. But outside of that space, there are also a lot more emerging techniques coming out, which are simplifying the training of spiking neural networks, making it more computationally tractable, making it much faster and making it easier to achieve a result with high accuracy. And within our SDK, we have the ability to actually pull in all of these techniques from the state of the art and really plug them in and utilize them alongside the standard workflow.
Okay, just about quick time for maybe one more question I had on, do you look at it in terms of the effective precision with the weights and the D-Day converter? What precision are you applying there?
When we consider the weights, what we realize is that you don't really require very high resolution synaptic weights. Very often we've seen 6-bit weights doing just about enough in terms of the neural network performance. And for our D2A converters as well, that is effectively the resolution that you'd see.
Got it. So it's a fascinating topic. We're out of time. You'll be in the breakout session later, and
yes,
everybody can join there to ask more questions. So thanks for introducing your architecture and great presentation.
Thanks a lot, Mike.
Okay.